This is lecture number 10. In the previous lecture, I extended the discussion of the three postulates of the quantum mechanics, and then especially we continued to consider the third postulate, which is related to measurement. And one of the most intuitive example was the polarization measurement. And then uh, at the beginning, you might you might feel that the measurement of the polarization can be most of the phenomena of the polarization measurement can be explained classically. So why do we need quantum? And then as we consider the extreme case when there is only single photon coming into the measurement device, then there was some problem with the classical picture. And once we introduce the concept of the quantized photon, then the overall all the situation can be explained in a single frame. So that's why we need the quantum mechanics. Next, I also introduced about the uncertainty principle. Most of you are already familiar with the the expression uncertainty principle. And what the uncertainty principle says is that in a typical quantum mechanics, when you learn about the uncertainty principle, the most popular example was the measurement between the position of the particle versus the momentum of the particle. And what the uncertainty principle says was, if you are trying to um, reduce the uncertainty in the measurement of the position, then the uncertainty in the um, momentum measurement will be increased, and then they have a reciprocal relation. So and then it can be proven mathematically, but there was no good insight in such kind of explanation. So instead of using the position position versus momentum measurement, I introduced the measurement of the polarization in terms of the HV basis versus the DA basis. And then once we consider these two types of measurement, then it is obvious why we have the problem of the, or why we have the limitation of the uncertainty principle, because the single polarization cannot be um, cannot be measured without any uncertainty, both in both HV basis and the DA basis, because once we um, once we fix the measurement of the measurement in the HV basis, then it will be either H or V. And in terms of the DA basis, it is completely 50-50 mixture of the D or T and A vectors. So there is no way you can tell anything about the anything about the V in terms of D or A basis. So yeah, from that perspective, the uncertainty principle makes sense a lot, and it is also obvious such kind of uncertainty limitation comes when two types of measurement do not commute. In this case, it is the maximally not commuting, because you can see that once we do one of the measurements, then the other measurement will be completely random. The next concept I started to discuss was the main topic of this subject, which is a quantum bit. And a single quantum bit can be general. Any arbitrary single quantum bit can be expressed in with this form, and then in this expression there are only two degree of freedom, which is theta and phi, and then mathematically this is complete enough. but it is not easy to visualize what happens. So instead of writing in this way, we also introduce the concept of the block sphere, which means that each of the superposition state will be mapped to one of the point on the sphere. The next concept was the single qubit gate, and I mentioned that the single qubit gate is similar to the NOT gate in the digital logic, and what that means is that the NOT gate changes or affect only one bit, and then single qubit gate is the similar thing. So even if there are multiple qubits, the effect of the single qubit gate is changing only one of the qubit, and but compared to the digital NOT gate, there are several types of single qubit gate. So I introduced the notation of XYZ gate and Hadamard gate. And one of the important property of the single qubit gate is that it corresponds to a rotation on a block sphere. So if when you don't understand when you get confused about the meaning of the each of the single qubit gate, if you visualize that single qubit gate in terms of the block sphere rotation of the block sphere, then sometimes a lot of things start to make sense. In today's lecture, I want to extend the concept of what we learned previously. So previously, we only dealt with a single qubit. So, but yeah, we know that a single qubit doesn't. We cannot do much things with the single qubit. So we want to extend to the concept of the multiple qubit, and then let's assume what kind of problem we will have if we start to consider more than one qubit. Well, you can imagine that a single qubit is represented by a single atom, like this one, a simple two-level atom, and another two-level atom. Yeah, so each of them are very good qubit, as you know, and then each of them has its own vector space. So there is no problem. Yeah, so but it is something like um, so this means that qubit A has its own space, while qubit B has its independent vector space. So it's almost like um, qubit A is sitting in my office, and then qubit B is sitting in the next office. So they are completely independent space. So that might just work as it is, but there is some problem. Let's assume that we want to consider some kind of interaction between two qubits, or in logical term, let's assume that we want to do some kind of conditional operation. What I mean by that is, let's assume that if the content of the qubit A is 0, or the qubit information stored in the qubit memory is qubit memory A is 0, then we don't want to change the value of the qubit B at all. However, if the qubit A value is 1, then we want to swap the information between 0 and 1. So it is more likely, so it is similar to the NOT gate in the digital logic, but the problem is not always applied to the qubit B, but it is conditionally applied, and then that condition is determined by the value of the qubit A. So it is called as a controlled NOT gate, and then the truth table looks like this one. So for example, if the value of the qubit A is 0, and then in this case, we can think that the qubit B, the value of qubit B is either 0 or 1, then the output or the resulting, the output state of that controlled NOT gate is that control won't be changed because control is controlling. It is not the target of the operation. So control still remains as control, the same value. However, the output value will be, and then in this case, because control qubit is 0, so it does not apply the NOT gate, but it will just apply the identity operator, which means that 0 will 0 and 1 will 1. On the other hand, if the value of the control bit is 1, then that means that, yeah, for each of the B value of 0 and 1, then the NOT gate will be applied to each of them. So 0 will turn into 1 and 1 will be turned into 0. So that's the logic table for the control dot. And control dot is frequently shortened as a CNOT gate, as a, for a short name. So I will frequently say a CNOT gate, and then not only by myself, and then you will hear a lot of CNOT gate whenever you hear about quantum computing. And now, yeah, there is some conceptual problem. When I said that um, uh, if we only consider the situation when there is no interaction between qubit A and qubit B, then they can be living in the two independent vector space. So yeah, this vector space just have some kind of vector which is completely independent of the vector in this space. However, once we start to consider this kind of interaction, then any kind of gate should be represented as a unitary operator. And then what do we mean by applying the unitary conditionally between these two qubits? So we cannot think about the unitary operator which will work only on the qubit A, and then there will be another completely independent unitary on qubit B. But we should somehow consider a bigger vector space which will contain both of these qubits. So if we succeed in building or constructing such kind of larger vector space, the vector in such kind of larger expanded or extended vector space will look like this one. So yeah, in that extended vector space, we need some kind of a basis, and then that basis, what we can think about is what kind of basis we might have. We probably have some basis which will have qubit A0 and at the same time qubit B0. So we might have this kind of basis, but that's not the only option because we have 4 different combinations for 2 qubits. So each of them might work as a basis. And then, yeah, I just say might because I didn't define whether they are orthogonal to each other. And then, yeah, whether I even didn't mention whether they are linearly independent. So yeah, let's see how we can combine two vector space into a larger vector space. And then yeah, let's think about the mathematical rule to combine those two vector space. To extend the two small Hilbert spaces, like combine two Hilbert spaces into a larger Hilbert space, we use the mathematical tool of something called as a tensor product. And probably you are familiar with the terminology tensor in other contexts like TensorFlow, which is popular tool in machine learning. And then the mathematical concept of the tensor in both cases are the same, but the way we utilize is kind of different. So yeah, let me explain what we mean by tensor product in this case. Well, I said that we want to, we would have the two Hilbert spaces, and then for example, qubit A will leave its own Hilbert space. Let's say that it is a V, for example, and then yeah, so this is a vector space where the vector leaves the in the vector representing the qubit A lives in this space, and then for the qubit B, there will be also corresponding vector, and then that vector lives in the W space, for example, W Hilbert space. In this case, in principle, we should be able to combine these two spaces and then create a new space and then a new Hilbert space. And for that case, we use this kind of notation, and we read this one as V tensor W. And what I want to prove is that the newly created Hilbert space has the dimension of Mn if the original V space has the dimension of M and the original W Hilbert space has the dimension of N. The proof is kind of straightforward. Yeah, let's first define who belongs to the tensor product space of the V and W. The elements of the tensor product of V and W space are the linear combination of the tensor product and tensor product vector, which is the which is composed of two vectors, tensor product of two vectors. Each of them came from each of the corresponding space. Yeah, so this the first vector came from the first Hilbert space, and then the second vector came from the second vector space. And in this case, what I can prove, what I can show is that if similar to this kind of tensor product of two vectors, I can consider the basis of this tensor product space. Especially, we know that in each of the space there are some orthonormal bases. So yeah, if I assume that vector space V used to have the three three orthonormal bases like 0, 1, 2, and then if the second Hilbert space W has the two bases, orthonormal bases like A, B, then the tensor product space V and V tensor W will have the basis vector, which is the tensor product of each of the combination. For example, like this one, and then for one, there will be also A and B, and so forth. Yeah, so there will be total three of the tensor product bases, and I can prove that any arbitrary vector in this tensor product space from tensor product space of V and W can be always expressed as the linear combination of all these vectors. And the proof is straightforward. The definition of the qualification of the element in this tensor product space is that each of the components should come from the V and W. So for example, we might consider V1 vector from V space and then the W2 vector from this space. In this case, we know that each of the V1 will be definitely composed of the V11 plus, well, let's use 0, V10 and V11 and V122, something like this one. And the W2's, yeah, let's W1 space, one vector. Then W1 vector should be also expressed as the linear combination of A and B bases. Yeah, something like this one. And then for this one, we know that this can be eventually expanded as the distributed law. Yeah, so it is V10, W10, W1A, 0 tensor product A, and the second this will be multiplied to a tensor product to here, then it will be V sub 0, 1, W 1B, and it will be 0 tensor product B, and so forth. So we will have the 6 terms, but it is obvious that all this kind of any vector will be represented as the summation of all these 6 vectors. And similarly, we might consider another vector v2 and w2. Then it will be also expanded as a 2 0 0 1 0 v sub 2 1 1 and so forth. And then if we expand the second line similar to the first line, then it will be also expressed as the summation of 6 different terms. So if we add these two vectors together, v1, v1 tensor product w1 plus v2 tensor product w2, then we know that each of them will be superposition of six of these vectors, and then this will be also another linear combination of these 6 vectors. So the final result will be the superposition of these 6 vectors. So what this proves is that this vector space is closed under the summation or the addition of two elements. And then that is the first requirement for the vector space. So yeah, we can prove that this vector space is closed under the addition. Moreover, we can also see that any arbitrary vector inside this vector space can be always expressed as the linear combination of these 6 vectors, and then this the number 6 came from the product of the 3 and 2, 3 times 2. So yeah, that means that any if we find out the tensor product space out of 2 vector spaces, then the dimension of the new tensor product space should be the product of the dimensions of each space. So which will be m times n. So I can also prove that this one without too much of problem. Yeah. So yeah, let's consider more property. Sorry, yeah, it takes a while to erase all of this. Okay, and the next thing, yeah, and then yeah, I just showed you that this new tensor product space is closed under addition, but you should also be able to prove that this new vector space satisfies all the requirement for, or it is qualified as the vector space. And to prove that, you should just you should show that this new space satisfy all those 8 different requirements. Another important concept is the linear operator in the new tensor product space. And then how can we define the linear space in a linear operator in the new space? Well, let's assume that each of the space, because each of the space had its own vector space, it also has well-defined linear operator in each space. And let's call the linear operator in V space as A, and then the linear operator in the vector space W as a B. Then we can define a new linear operator which will work on the tensor product space, and then we would write in this way, which is A tensor B, and then now yeah, we should define how this newly defined newly combined linear space work on the vector. And then we know that any arbitrary vector in this space will be expressed as the V tensor W. And then if we apply this kind of A tensor B on it, then what happens is very straightforward. The linear operator A used to live in the V space. So the only thing which is defined for A is action on the vector in the V space. So we cannot think of any other thing, but the only thing we can think of is just applying the A operator on the vector V, which used to be the element of the vector space V. Similarly, um, the linear operator B was only defined in the vector space W. So yet we only know the action of the B on the vector inside the W. So and this W came from this W space. So yet this is well-defined part. And then we know that the application of the linear operator on the vector will generate new vector in the same space. So this is the different vector or different or the same vector depending on the operator. But this vector still lives in the vector space V, while this vector still lives in the vector W. So we know that the result of the linear operator, the newly defined or the um, tensor product linear operator um, combined by tensor product or generated by the tensor product still um, map the vector in the tensor product into another vector in the same tensor product space. So I know that this is a little bit too much to explain all of these details, but and then yes, if you hear this concept for the first time, then it might be confusing. But there is very simple idea. What I generally say is that the tensor notation really works like a partition. What what I mean is the following. So yeah, because it is if it is here, then it's not easy to see. So let me just write the yeah. Let's say that our tensor product of two linear operator is written in this way. Then, as I said, this tensor notation works really like a partition. So all I do is I should check the linear operator in the first partition, which is A, and then this one will work on the vector in the first partition, which is V. So the operator in the partition will act on the vector in the corresponding partition. So for this case, we were only considering the two tensor product from the two vector space, but we can because we can have several qubits. So if we have 4 qubit, then we should consider the four tensor product or a tensor product of four operator. In that case, we might have something like A, tensor B, C, and D. And each of the tensor works on different space, and then they will work on the V, W, X, sorry, Y, or something like that. But make sure that each of them are like a partition. So the first operator only works on the first vector, and then the second operator works on the vector only in the second partition, and then third operator works on only on the third partition, and so forth. So if you just follow this rule, then the product of the linear action of the linear operator is very straightforward. Another property, if we define well, um, another thing we should also consider is how this newly created linear operator will work on the linear combination of the vector in the tensor product space. So here we only consider the action of the result of the action on the single vector, but this is a linear combination, and of course the natural extension of the linear operator is that this operator should work on each of these components. So we know that this will be expanded as the multiple summation of the multiple term, and then this combination of A tensor B will work on each of the element. So yeah, I use the notation of the definition because yeah, you might define in different way, but yeah, we are not interested in other definition, but we are only interested in this kind of extension. And then it will be a very natural extension of what we learned up to now. And as I mentioned, yeah, for this case, we were only considering two vector space, tensor product of only two vector space. But as we consider more and more qubits, then we have to write down the tensor product of so many vectors. And then yeah, even for two vectors, it already requires a lot of effort. So in many of the situations, people somehow omit the this notation, and then in most of case you will see this notation, or even further simplified like this one with only comma. And in the extreme case, you will still see, well, not extreme case, frequently in quantum information, you will see this kind of notation. So yeah, let me show you this example. Yeah, so what this says is the first qubit is in the zero state, and then the second qubit is in the one state. And then, yeah, of course, this is the most formal expression. But again, yeah, people would prefer, would like to use simplify in this way or this way to make sure that each of the which number corresponds to which qubit. But it is quite obvious which one will be which. So we don't really have to label each of the number, but we might just declare that the value inside here, the value inside the cat corresponds to this order. However, in most of the situation, the order means which number corresponds to which qubit. For example, in the just the simple in the typical digital logic, we use the binary digit, and then once we write down binary number like 0, 1, 0, 0, sorry, what am I doing? Yeah, so 0, oh, sorry, 0, 1, 0, 0, 0, 1, 0, something like this one. Then we know that this is the most significant bit, and then this is least significant bit. And then we know that just by looking at the number, we know which digit corresponds to which position. So just writing down the number in order is more than enough. So as long as there is no confusion, people prefer to use this kind of most simplified notation. Now we are equipped with the mathematical tool for the tensor product. Let's consider some of the example. The first example is the controlled NOT or CNOT gate, which I already introduced. And then in that case, this is the notation. Here I'm assuming that there are two qubits, and then the one qubit, I will call it as a control qubit, which decides whether we will flip the information in the target qubit, and then the second one is called as target qubit. And in this case, this is kind of notation for the CNOT gate, and then this notation says that the black dot means that it is control, and then this is the target of the control part. And then whether this second qubit will be flipped or not will be determined by this control qubit. And then even if for this case we are drawing the circuit in the two-dimensional paper, what this really means is that this is the kind of time flow. Yeah, so in the typical digital logic, then we would have multiple gates. Then generally those gates will take the space. However, for the notation of the quantum circuit, they generally imply the state step after the time. Yeah, yeah. So yeah, this is the time step. So before the gate operation, we would just say that this is the input state, psi or sub input for the signal gate, and then I will represent the output state as psi output. Then the first example we can consider is the 0, 0 input state. Yeah, so here I'm using the tensor notations, meaning that the control qubit is 0 and then the target qubit is 0. And in this case, according to the um, truth table, then the output won't be changed. So yeah, this just turn into just a 0, 0. And I also want to point out that if you look at the this circuit, and then I said that this is similar to the digital logic, but there is extremely important difference between the digital logic and the quantum logic. And the thing is, even though yes, for the digital case, generally we would have something like AND gate or gate, and most of the gate generally has less um, output line than the number of the input lines. However, for this case, we always keep the both of the qubit, and then if the input of the some circuit is n qubit, then the output will be always n qubit. And there is some important reason why we need such kind of thing, because I mentioned that the operation of the quantum state, the evolution of the quantum state is only always connected through the unitary operator. And then unitary operator means that it is in principle, we should be able to recover the original state, because if we have some um, original state, and then if we multiply u, and then we will obtain the next state. But because it is a unitary, we should always be able to find out the um, Hermitian conjugate of the original operator. And then yeah, for the unitary operator, this corresponds to inverse operator. So for the unitary operation, we should be able to find out the inverse operation corresponding to that one. And then if we multiply the inverse operation in front of this one, then it is going back to the original state. However, if you think about the this AND gate, can you always be able to recover the original input? Generally not, because if this is 0, then there are three different possibilities, or 0, 0, or only one of them are 1. So only with this state, only with this information, you cannot reverse or invert the gate operation. So that's why the quantum state will always will have the same number of output qubit with and the number of qubit in the input and output will be always the same. Another state we can think of is the 0, 1 state, or 1, 0 state for the control and then target 0. In this case, the role because control is 1, we want to flip the target qubit, which we will, and then the final output result is 1, 1. So now what we can think is that what happens if our input qubits are 0, 1, 0 plus 1 tensor product 0. In this case, well, yeah, we should be able to expand this tensor product into this state. So this is the input state, and then the result will be the superposition of the corresponding output for these two input states. So yeah, the output state will be 0, 0, which corresponds to this input, and then plus 1, 1, corresponds to which is the output state corresponding to this input. So yeah, this is the output. and then you can see that the unitary because all the gate operations are represented as a unitary operator, and then because the unitary operator is linear, so gate operation will be always linear on the different state. Another example of the tensor product notation is Hadamard gate. Yeah, so let's assume that we have two qubits, and then we are applying the Hadamard gate on the first qubit first, and then the another Hadamard gate on the other qubit later. And for this case, how can we express this kind of evolution in terms of the qubit notation or the bracket notation? So let's assume that our initial state is a 0, 1 state in the A and B qubit. In this case, what we can here we first want to consider the case when the only the qubit A is changed by the Hadamard gate. So in this case, it can be expressed in this way. Yeah, so this is initial state, and then all I mentioned that this tensor notation or the linear operation on the um, tensor product of linear operation means that each of these kind of works like a partition. So yeah, this we know that we only want to change the qubit value, qubit A value, and then we want to leave the qubit value B on intact. So in this case, if we express the linear operator in terms of this kind of tensor product, then that means that the operator in the first partition will work on the first qubit, and then the second operator in the second partition will work on the vector in the second partition. So yeah, each of them will just work like this, and then yeah, this is the next stage, and then we know that identity won't do anything, so you're just another one. And then for the result of the Hadamard gate acting on the 0 state will turn into 0 plus 1 over square root of 2. And then next is how can we express from psi T2 to psi T3? Well, it is similar to this one, but now we have to apply the Hadamard gate on the second partition. Yeah, so and then yeah, I just bring this state into here, and then in this case, this first the identity operator will work on the first partition, and then it doesn't do anything, so it will just look like this one, and with the partition not partition, but yeah, it is tensor notation with the separation with the tensor notation. Then the Hadamard gate on the B qubit will work on the B state, which is 1. Yeah, so it will be something like this one, and then eventually this one will turn into 0 minus 1 over square root of 2. So this is a result. But if you can also think that for this case, we don't really need to separate this operation in 2 steps. For this case, you can just think that we can apply the both of the Hadamard gate on 2 qubits simultaneously. So if you just express in this way, then you will obtain this kind of output state. Similar that we have a matrix representation for each of the linear operator, we can also think about what will happen. What is the matrix representation corresponding to a tensor product, or the tensor product of the two operators? And then the conclusion is actually the matrix representation of the tensor product generally appears as the something called as product. Yeah, so I hope that I hope some of you are familiar with the concept of the chronic product. And then the expansion is quite simple. Yeah, for example, if we have um, um, 1, 2, 3, 4 um, matrix in the tensor product with 5, 6, 7, 8, something like this one, then the expansion rule is something like you have 1 times 5, 6, 7, 8, and then 2 times 5, 6, 7, 8, and 3 times the same matrix expansion. Yeah, so the rule is just um, put each of assume that each of the matrix is some kind of element, and then you just multiply each of them, yeah, inside. And then yeah, there is another example you can think of. Yes, for example, the corresponding um, tensor product of vectors can be also expressed in this way, and then you are just adding and inserting each of these column vector to each of the component. And also for the matrix, similar to this example, if you are if you are calculating the tensor product of two x and y operator, then all you have to do is multiply this y operator for each of the component, and then you will obtain this kind of result. If we get back to the discussion of the control dot gate, there are a few things we also want to discuss. First of all, control dot gate is, in some sense, some people say that this is kind of quantum version of XOR gate, because the output state behaves like this one depending on two values, and then if you remember the behavior of the XOR gate, it becomes only one when two of the two of the if the two input values are different. So for when they are the same, then the XOR result will be 0, and then when they are different, then the XOR result is the 1. Yeah, but you should not take it too seriously with this kind of analogy. And then um, yeah, and one more thing I want to discuss is that what is the universal gate in the quantum gate? Yeah, and then yeah, what is the meaning of the universal gate in the classical digital logic? And then if you learned about the digital logic design class, then you learn that any arbitrary digital logic can be always constructed by combining only the NOT gate and OR gate, or NOT and AND gate. Yeah, so yeah, those are the universal gate. But moreover, you also learn that the NAND gate by a single NAND gate can be also turned into the yeah. So NAND gate also can produce the NOT gate or AND gate. So yeah, eventually, all you need to implement the any arbitrary gate is the NAND gate or NOR gate. Yeah, NOR gate has a similar property with the NAND gate, but the concept of the universal gate means that what is the minimal set you need to construct any arbitrary gate, and then in the quantum gate, similar concept is applied, and then in quantum circuit, the universal quantum circuit for the universal gate for the quantum circuit is that all the single qubit gate, and then one of the two qubit gate, and then the two qubit gate means that similar to the control NOT gate, depending on if the gate cannot be just written as the tensor product of the two operator, then they are generally called as a two qubit gate. And then in that case, you should always be able to find out the combination of the 2-qubit gate, and then one of the 2-qubit gate, and then the single qubit gates. So those are the universal gate. And then the another property of the CNOT gate is that it should be unitary, because we know that all the quantum gate should be unitary. And then unitary also implies that it should be an invariable gate. Then how can we prove that it is unitary? Yeah, first of all, how can we represent the CNOT gate using the tensor product? Well, yeah, that's actually quite straightforward, because all we need is when the control bit is 0, then we don't want to do anything on the target qubit. So if you have this kind of term, then whenever the vector has the 0 in the first qubit, then it will be this will be multiplied, and then the term, the control term, control qubit will still 0, while the action of the target qubit is just identity. Yeah, so that it won't do anything. On the other end, if we also have this term in the entire expression, then if the control qubit is one value, then yeah, this one regenerate the one vector, but the target qubit will be changed by this X operator. And also another and yeah, and based on this relation, you can also find out the matrix representation corresponding to the control NOT gate, and then if you just use what we learned before, then as we learned, well, this part can be represented as 0, 0, 1, 0, 0 matrix, and then this is just the identity operator, and this one can be the representation, matrix representation of this one cat bra state, or the operator can be represented in this way, and then we know the expression matrix representation of X. So yeah, if you just use the rule which was shown in the previous page, then you should be able to reproduce this one. And then once we have the matrix representation, it is obvious that this is the universal gate, because if we take the Hermitian conjugate of this one, then well, yeah, dagger is not pretty. Yeah, so yeah, if we apply the dagger to the Hermitian to this matrix, then because there is no complex number, so we don't have to consider about the complex conjugation. But the Hermitian conjugate means that we should also do the transpose. And then if we transpose with respect to the diagonal element, then they won't change. So the Hermitian conjugate of this one is the same as its original matrix representation. And if you multiply the same matrix twice, then they will turn into the identity operator. So based on that fact, yeah, we know that CNOT gate is unitary gate. Generally, there are a simple way to construct a linear operator in the tensor product space. And then I showed you that if you just combine two linear operators from each of the space, then this will be a good linear operator in the tensor product space. But there is also similar to what we saw with the previous page, similar to the control NOT gate. Yeah, we can also construct construct new linear operator on the tensor product space just by linear combination of the tensor products of the operators. So yeah, if we just add them together, then it will be a new tensor product. And then in this case, the way it operates is similar to your intuition. So because it is a summation of multiple terms, so it will act on the vector um, linearly. So yeah, this is the kind of definition or requirement for the linear combination of the tensor products of the operator. And then yeah, the good example was the control NOT gate, which I just show you in the previous page. Finally, as we discussed in the early lectures, like lecture 1 and lecture 2, yeah, vector space also can have the inner product. And yeah, of course, the vector space by itself doesn't really have to have an inner product, but once the inner product is defined, then there are a lot of interesting property. And then I claim that we want to produce the new Hilbert space by combining the through the combination using with the tensor product. So we want to have a well-defined inner product, and then inner product also requires some special properties such as skew symmetry. So what's the good way to define the inner product in the newly created tensor product space? And the answer is a little bit straightforward. So yeah, we know that if we have some something like psi tensor product phi, then we know that the corresponding bra vector is the psi tensor phi. So yeah, the newer the bra vector corresponding to this new cap vector is something like this one. And then in this case, if I just have to multiply some phi pi with some x y. Oh, sorry. Something like this one, then yeah, similar to the linear operator, we can consider that each of these tensor product notation means the partition. So the first part, the first bra will be multiplied on the first cat, and then the second bra in the second partition will be multiplied to the cat vector in the second partition, and so forth. And then once we multiply each of them, then we also multiply the inner product of each of the space. So that's the definition of the inner product, and then that is well qualified as the inner product operator in the tensor product space. Another notation we frequently use is the this kind of exponent shape. And then what this means is that we are considering psi in both spaces. And then if we have k qubit, then we can think about the state where each of the qubit has the same state in for all of the qubits. Yeah, so in that case, it will be expressed in this way. And another thing is, if you remember our one of the example with the two Hadamard gate acting on the two qubits, then yeah, such kind of situation can be expressed in this way, or yeah, in this way. And if we have k qubit, and if we want to apply the Hadamard gate for all those qubit, then yeah, this will be a simple notation for such kind of situation. So yeah, I will stop here for today's lecture.